My name is Pratyush Sajjad, and I'm a master's student at University of Illinois Chicago. For the past, I'm actually graduating this month. To be honest, I'll be graduating tomorrow. Tomorrow's my final date as a master's student, and thank you. And yeah, for the past 2 years, I've been trying to expertise in deep learning and machine learning models, and to be precise, more towards computer vision. And I started interest in stereo cameras, stereo depth estimation models, and that's how I started my master's thesis a year back. I did it under my advisor, Professor Ahmad Anish Chatin, is from University of Illinois Chicago as well. And so today I'll be presenting a part of my master's thesis, and it's titled Improving the Efficiency of Stereo Depth Estimation using Walsh Hadamard theorem, Hadamard transforms. So the basic idea here is to use Walsh Hadamard transforms, which is a type of transform like Fourier transform, to see if it's making deep learning models, machine learning models like transformers and convolutional neural networks, if it's making more efficient. So we'll start with the outline of the presentation goes like this. I'll start with the introduction and the problem statement, followed by the background, for which we would need to understand what stereo geometry, the metrics, and the data set that we'll be using. And for chapter 3, we'll be looking at a model called stereo transformer. And chapter 4 is where we'll be looking at the Walsh Hadamard transforms, followed by its implementation. And chapter 6 and 7 is the results and the takeaways. Starting with the introduction, so the main motivation here is that stereo depth estimation, or depth estimation in general, is fundamental for missions to understand 3D spatial relationships in the real world. The two main techniques that are widely being used today are LiDAR, time of flight, and stereo cameras, as you guys know. So LiDAR is, as you can see, it's like huge, and it's not really cost efficient, even though it is better in accuracy, but the hardware is not cost effective. As you can see, it's really big. That's on top of a car, and you can see how big that is. And it also produces sparse point clouds and not dense ground truth. So that's a problem with LiDAR sensors. And if you look at stereo depth estimation, it's a stereo cameras. As you can see on top, it's just like normal cameras that we see in our smartphones. And they offer comparably better accurate results with just 2 cameras, making it highly cost effective and easier to productionize. And some of their applications include autonomous vehicles, as we all know, robotics and industrial automation, medical and surgical applications, augmented and mixed reality, security and surveillance, and 3D reconstruction. So the problem statement, as I said, is that these models are very heavy because they consist of 3D convolutional neural networks, transformers, and they help in achieving high accuracy, but they are also cost high max and high memory latency. So they block deployment on resource constrained edge devices. So my research question here was, can we reduce compute and energy in a transformer-based stereo neural network pipeline without sacrificing any accuracy? And for that, we'll look at the background for stereo depth estimation. And for that, we need to understand how a traditional camera works. So a traditional camera would, as you all know, take 3D coordinates from the 3D world and convert it into 2D coordinates on the image plane. And if we try to bring back the 3D coordinates from the 2D plane, it's not possible because it's just a single camera. But it could be made possible using a stereo camera setup like this one. So a stereo camera setup is when 2 cameras, one camera on the left and another right camera that's displaced at a certain distance. And that distance is pretty important because it's called the baseline that could make things, a lot of things depend on that. And by if using this setup, when you take images simultaneously, you get a stereo pair of image, which might look identical, but if you look closely, you could find a small shift in pixels, and that shift in pixels is called disparity. And with the help of that disparity, we can find the depth of any object within that pixel from the image plane. And how we do that? We can use that equation where z is the depth and f is the focal length of the cameras, b is the baseline, and d is the disparity. Using this equation, we can find the depth of any object that's in front of the camera. And this is an example of a stereo pair of image. They might look identical, but one's taken from the left camera and the other one's taken from the right camera. As you can see, the car, the object, is moved slightly to the left on the right image. So that shift is called disparity. The higher the disparity, the closer the object it is. So it's inversely proportional to depth. And baseline is directly proportional to disparity. So the longer the cameras are from each other, the more detail you could obtain from them. And some common problems with stereo matching is that surfaces with repetitive textures, like a piece of paper, a brick wall, or a fabric. So these are some issues that traditional stereo depth estimation models faced. And for our model evaluation, we use two types of evaluation. One for the accuracy, which is endpoint error, which is basically used for almost every stereo depth estimation models. It's just the predicted minus the ground truth and the mean of it. And bad pixel rate is the percentage of pixels over a threshold tau. And on the right side, these are the metrics that are used to verify the efficiency metrics. So for that, we use multiply accumulate operation max, which is just one multiplication followed by one addition. And flops, floating point operations, is the count where we count them individually. So one max is equal to 2 flops. And gigaflops or gflops is 10 to the power 9 flops, which is a standard reporting unit for neural network inference cost. And for our model training, we used stereo Carla dataset. It's a very high quality dataset where we were able to achieve like 1 meter baseline, which is pretty rare. And the resolution is used is and the resolution for the dataset is 1600 by 900. And it also had dense ground truth disparity from LiDAR simulation. And that's an example of the left and right image followed by the disparity ground truth map. And going on to chapter 3, stereo transformer, it is the model that we will be experimenting with. This is from a paper from 2022. So since it's from 2022, we had to make a couple of changes to the baseline, and we'll see what they are. So STTR is, or stereo transformer, is a type of vision transformer. They are known for replacing the memory intensive 4D cost volume with global attention based matching. And this is the first stereo depth estimation model to introduce a transformer. This makes it particularly good at handling repetitive thin structures and occluded regions because attention reasons globally over the entire image rather than local pixels. And the reason to choose this is just like every other transformer model, it has a self cross attention layers within them, and this is the area of interest for our WHT implementation. And that's an example of how the inference worked with one of its pre-trained models. We tried to inference it with the stereo color dataset, and those are the results. So this is the architecture of the stereo transformer. Just like any other vision transformer, it takes a left and right image pair, and we run it through the feature extractor. The feature extractor is a set of convolutional layers which would downsample the image to 1/8. And then before going into the transformer block, we had to positional encode them so that we know where each tokens belong. And after that, we send it to the transformer where the self-attention would, so in the self-attention you just attend to itself, and in the cross-attention layers both the images would just share information between themselves. And then it would develop a cost function. So cost function is the final disparity, this is how the final disparity map would look like, and that goes into the regression head and we would get the disparity map out of it. And this is the self-attention is where we are going to target the WHT integration, because as you look, the main self-attention is where the most of the flops takes place. So we try to implement the WHT there so that we can see if it performs any better. And for chapter 4, we will be looking at the Walsh Hadamard transform itself. And so the Hadamard transform is just like the Fourier transform, but instead of having complex numbers in its matrix, it will just have plus or minus 1. So that's an example of a 2 cross 2 Hadamard matrix, where you can see it's all plus 1s except for the right bottom one. And that's an example of the 4 cross 4 Hadamard matrix. And what's the benefit of using a Hadamard matrix is it's that it just has plus or minus 1 values in its matrix. So there's no need of multiplication in the transform like in the Fourier transform, because in Fourier transform there are complex values and you would require multiplications there, unlike here you just don't require any multiplications. And it's orthogonal and symmetric, and the inverse is pretty simple, you just apply it again and divide by n. And this is the WHT mix, the mixer which would replace the self-attention. So here we would take, in the first you can see Z and X is the input, and Win is a learnable parameter, and this is the entire WHT transform. Here you can see Z, which comes from here, gets transformed into the frequency domain, and we multiply it, we element-wise multiply it with a learnable parameter. We call it GC here, and we do that. We do the entire thing inverse to bring it back to the spatial domain, and we do this. So for the first layer is for the channels, and the second layer is for the tokens, and for the final layer we just have another learnable parameter called WOut, and it's all completely multiply free in the frequency domains. Why Walsh Hadamard transforms and not Fourier? As I said, you can see the Fourier transform, the Fourier matrix, it's full of complex numbers, unlike Hadamard matrix, it's just plus or minus 1 values. And what does each stage do? The self-attention, we all know it just does the global content spread, and the cross-attention would just do the left and right correspondence. And for the implementation, we used the stereo Carla dataset with a resolution 512 by 1024. We trained the baseline and the updated model to 250 epochs with the Adam W optimizer. And we can look at the results. So these were the results that we were able to obtain for the baseline, and on the right it's the WHT integrated model. We were able to get 3% reduction in the parameters, which might not look like a lot, but when you look at the G flops, we were able to achieve almost 60% reduction from 348 to 142. And latency from 95 milliseconds, we were able to bring it down to almost 36 milliseconds, which is 62% faster. And from 10 FPS, we were able to make it up to 27.8 frames per second. And we were able to achieve almost the same EPE. So for EPE, the lower the better. We were able to achieve 0.02% better, but it's negligibly better. And we also fine-tuned it with Kitty dataset, where the baseline was performing better than our model. And these are some of the examples of the outputs from our both of our trained models. The one on the left is the left image of stereo Carla, followed by the ground truth, and that's how our baseline model performed, and followed by the WHT1. And we also tried if it's just for stereo or it would generalize beyond stereo. And we trained it with, we tried the WHT mix with image classification and a text classification test. And we were able to achieve 4.3% reduction in G-flops in the image classification task, even though there is some reduction in accuracy. And for the text classification task, we were able to achieve 13.8% reduction in G-flops with a little reduction in accuracy. So the main takeaway here is that we are able to achieve 2.46x compute, 2.75 times faster inference, and matched accuracy. And with that, I would like to end. And before that, I just like to tell you guys one thing. Harpreet was telling about if you have any products, you could advertise them. I don't have any products to advertise. I just have myself to advertise. I just completed my master's, and I'm looking for opportunities. So if you guys have any opportunities for machine learning, deep learning engineers, I would be happy to connect with you. So that's my LinkedIn profile. So if you guys can scan and